Okay, so I am talking about the project. It's a dynamic analysis that was conducted on a poorly mixed heater tank to evaluate its ability to operate under PI control at design conditions. The tank does not behave as a single wall mix system, therefore we're modeling it as two continuous stirred tank reactors with an internal recycle loop. And we're applying a step change in the steam valve position. It's applied during the test run at a reduced flow rate of 105 liters per minute, and the resulting temperature responses were used to identify the system parameters. Um, so that's just the first part of my hand calculations. But if we're just looking at like the full process diagram, this is including the control loop. It's a TS control system for T1. So it's essentially the same block diagram that we had earlier, except we're also adding a GC of S in this feedback loop of GM. And you can also, like, once again, use the loop law to simplify that flow sheet. And we can get down to here, the simplified block diagram. And this part here is the same as what it was earlier in the project, but now we're adding this part up here in this GM loop. And then I have my mapping table for my variables. These are just the variables themselves. These are the first order variables, and these are the second order variables. All of these were plugged into my Excel sheet to calculate for them so that I could plug them into Simulink. I modeled my Simulink after this guy because I thought it would be easier. I'm not sure if that actually was easier, but oh well. Um, the valve dynamics were characterized using a first order model, and then from the valve gain and the time constant were determined. KV is zero point 0.8 and tau V ended up being 1.11 minutes. Process dynamics were then modeled with the two first order systems in series, as I just showed. They're using dynamic data fitting, and the time constants were estimated for tau 1 to be 1.47 minutes and tau 2 to be 0.73 minutes. And then KP was found to be 1.28. KP was calculated from the QR test and the QA from like the initial test values I had. I'll show my Excel document in a second. But those parameters were used to construct an equivalent second order model, yielding tau prime as 1.1 minutes and the damping ratio of zeta. I think that's zeta prime to be 1.13. Physical parameters were determined using energy balance relationships. The overall heat transfer coefficient was UA. UA is the overall heat transfer coefficient, that ended up being 3,360. The mixing volumes were calculated. V1 is 1329 liters, and V2 is 4,670 liters. In the internal recycle flow rate, QR ended up being 800 liters per minute. Those values are consistent with the observed slow mixing behavior near the heating coil. The model wasn't scaled because we start with the initial conditions, the lower one, and now we're scaling up to be 500 liters per minute, and they were adjusted proportionally to flow rate, resulting in a reduced dynamic response times. The required steam temperature to achieve the desired outlet temperature of 75 degrees Celsius from inlet temperature of 25 degrees Celsius, TS ended up being 110.7 degrees Celsius. The controller design was performed with Simulink. KC was found using a gain block in place of like GC FS, and I manipulated the gain to see when constant oscillations were achieved. I'll show that in a second as well. And the gain input became GC max, the value that I was putting in the gain block that ended up being KC max. And PU is the period of those oscillations found, which ended up being 3.81 seconds, and the corresponding omega U was found to be 1.65 radians per minute. A KC actual is found to be 6.19, and finally, based on those values, the recommended PI controller settings are KI to be 1.95 and tau I to be 3.18. KC was 619. And then we're looking at the closed loop to find a response of 10 degrees Celsius for the inlet temperature in Simulink. I used a step input to model that, and the maximum deviation in the outlet temperature was found to be 6.35. Yeah, to 10 to the negative 1 degrees Celsius at 2.34 seconds. That provides acceptable disturbance rejection under the design conditions. And overall, the two-tank recycle model provides a reasonable representation of the system dynamics. MPI controller was able to achieve stable and satisfactory performance with the intended operating conditions. These are my calculations from Simulink that I was finding for like omega and Kc and tau I. And these are the relationships I had to find for the gains. To look at my Excel sheet, this is the design. KV and tau V calculated here. These are my volumes and UA. These all are my first order response, second order response, and these are all of the A's and K. These A's go into calculating the new T1. This was the graph I was getting to find the stable oscillations. And this here is where I was calculating for the maximum output deviation with the 10 degrees step input. And in this spreadsheet, that's where I was calculating for KV and all those fancy fellas. And over here is where I was finding the step input change. We got the 110.7 degrees Celsius. Thank you.